All right, so where we left last time is we had created this fictitious, I guess it's the fictitious potential that is associated with this situation. And we noticed that all of the physics was wrapped up in the fictitious piece of the potential, unlike the classical case where you have a physical potential. There's no longer this physical potential, but we have this fictitious one. And the fictitious one has these various shapes. And the shapes are associated with two distinct numbers: the reduced angular momentum, which we called h hat, and the total energy per unit rest energy of the infalling particle. And between these two numbers, we can describe the entire physical situation we're dealing with. And the point of this lecture is to do that, to get intuition on how to understand this drawing. And the reason is because people get familiar with this mathematically and they don't translate it directly into the situations at hand. And I think it's very, very helpful to do that, to understand how these two numbers establish the physical circumstance that's actually happening. So we'll have a look at that. Before we begin, we should understand these numbers as a reminder. Remember, h itself is in units of length. You can go back to its definition to see that h has units of length. So h over alpha will be dimensionless. So this is a dimensionless unit, h, the reduced angular momentum. And this is going to be the total energy of the falling object as divided by its rest energy. So that's basically a way of saying the kinetic and potential and rest energy in the numerator, and then the rest energy in the denominator. So if you have no kinetic and no potential energy, this is going to be E0 over E0. The only thing, you can't get away from your rest energy. So if you have no kinetic energy, meaning you're motionless relative to the center of symmetry of our problem, and you have no potential energy, which means you're so far out radially, right? Your distance is so far that this expression is zero, right? If you look at it, the larger rho gets, if rho is really large, this side becomes 1. If rho is really large, this side becomes 0. So you have 1 times 1, the square root of 1. You have v equals 1. And the reason it equals 1 and not 0 is because this, if you remember from the last lecture, was actually the potential energy per unit rest energy also, right? The right-hand side and the left-hand side need to be the same. So we had rho dot squared equaled kappa squared minus v squared. And this is energy per unit rest energy. So this is potential energy per unit rest energy. And this is kinetic energy per unit rest energy. And so this limits to 1 in long range. What makes everything very, very special is that this potential has this cusp on the top, right? Because we know from the classical case that this curve here would just continue up forever and would never peak out. But it would be very similar in the classical case down below here, where the shape of this curve is the same. So what we want to do is we kind of want to understand how to picture the situation for understanding how we can derive from just the reduced angular momentum and kappa, the physical situation that's happening. So the first thing to understand is that once you pick an angular momentum, which is conserved in our problem, which is constant in our problem, once you pick that, you have basically chosen what potential curve is relevant for the problem. So in this picture, what we've done is we've graphed several potential curves for different angular momentums. But if we consider a case where angular momentum is completely conserved, meaning we're not turning on rocket jets and changing, or rocket motors and changing directions and speeds other than just falling under the influence of gravity, only one of these curves is in effect at any given time. And let's just consider this one here, h equals 2.2. So I've bolded it out. Now the other curves just don't matter right now, because once the angular momentum is set, it's constant. And this is the potential that is seen by our falling body. So now that we've selected that, we have to say, well, what kind of circumstances could achieve that particular angular momentum? Now, let's say this is a relatively large reduced angular momentum. So we're looking for circumstances where we have large angular momentums. Well, what kind of circumstances are those? Well, if this is the center of if that's, say, the black hole in the center of symmetry, we can now imagine a particle, which I'll depict in blue, being very, very far away. We know if that particle was headed straight towards the black hole, it would have zero angular momentum relative to the black hole. So that's not our circumstance. So we can also imagine the particle would be traversing, I guess if you drew a line between the particle and the black hole, you could imagine it has a velocity vector that is highly angled away from that, from the line connecting the particle with the center of the black hole. That would have a relatively large angular momentum. And the faster this particle goes, the larger h would be. So you can increase h by increasing this angle and increasing the kinetic energy of the particle. You could also have an arbitrarily large h without a high angle. You could have a very shallow angle relative to the line between the particle and the black hole, as long as the velocity vector is big enough. If the velocity vector is big enough, then the cross product between that velocity vector and the sort of the impact parameter, or I should put that's probably not a good way of talking about it. The perpendicular distance of the projected straight line, we would say, perhaps, that could be very, very large as long as the velocity is high, right? If the velocity is high, right? So high velocity with small impact parameter will give you an h, will give you a high h, and also low velocity with a high impact parameter will give you a high h. So there's many ways of being of our particle or our falling spaceship without any motors on, of experiencing this particular potential. Whatever way it chooses, once the angular momentum is set, the potential is set. Which one of these circumstances is in effect, whether it's this one or this one, is dependent on the second number, the energy, because the energy the energy of the spaceship is really going to be wrapped up in its kinetic energy, and the kinetic energy will be wrapped up with the velocity. So a high kinetic energy will be a situation more like this. A low kinetic energy will be a situation more like that, more of a slow-moving object that's actually whose path of motion is quite perpendicular to the line connecting that object to the center of symmetry. So that energy is reflected in this number right here. This number here is actually K. I used E because I wanted this to look a lot like Meissner, Thorne, and Wheeler's picture, just sort of stretched out a little better. Meissner, Thorne, and Wheeler used rho over m instead of rho over 2m, and therefore the event horizon is at 2 instead of at 1. Right? If rho was equal to alpha, then you would have alpha equals 1. That's how I would have done it. But they have, Meissner, Thorne, and Wheeler goes rho over 1/2 alpha, rho over half alpha. So you need rho equals 2, right? So anyway, that was just me trying to mimic the book so that the graph would look similar, and I left it that way. But so choosing K basically determines the physical orientation of the falling body with respect to the black hole. So if K is very, very low, and by low we mean if K is very, very close to the rest mass of the particle, which makes it equal to 1, then you have this lowest possible. It's like you had a particle that was very, very, very far away from the black hole, and you let it go, and it started falling in. It would be the applicable elements of the graph would be E equals 1 and H equal to 2.2, because it's far away from the black hole, but you must have given it a push, enough of a push to give it a significant angular momentum relative to the black hole, but it's still very far away and moving extremely slowly. So that would be an example of this circumstance here. However, if you moved it extremely quickly and you pointed it very close to the black hole such that h was still 2.2, then you would be dealing with a situation that might be, say, up here along this line. Right. And so each of these physical situations is completely dependent on these two numbers. And you should be able to look at this graph and say, okay, this is the physical situation of maybe a wide flyby orbit, and this is the situation of a very close flyby orbit. The reason we know it's a flyby orbit is because if it's coming in, remember, these are the radius direction. This is the radial variable, right? So it's approaching and it's accelerating because this potential you can treat it classically, right? The force, the gradient, the opposite of the gradient of the force is going to actually accelerate the particle in, and then it's going to reach this turning point. It's going to reach this turning point, and then it's going to retreat. And that's exactly what a flyby orbit should do. The particle would start, say, right here. It's got a very, very slow movement, but it's a relatively significant impact parameter. It accelerates. It reaches that turning point, which is depicted right here. That radial distance is this distance right here, the perigee of the motion, and then it goes off to infinity again. That would be the classical, and this would be a classical orbit, right? I've kind of drawn it like a hyperbola. It still remains to be seen exactly what the shape of this orbit's going to be in our general relativity situation. I'm not making any promises, but I can make a promise that it will be a flyby orbit if it's anything lower than this tip and anything higher than 0, because those all show particles that are moving in and are pulled in from infinity and hit a turning point and turn around and go back to infinity. So we call those flyby orbits. Then, but you could, in this circumstance, not in the classical circumstance, right? I already mentioned the classical circumstance, this curve goes up forever. So every orbit in the classical circumstance above 0, every orbit above 0 is a flyby orbit. So flyby orbits go all the way up to forever in classical circumstances. And the higher angular momentum you get is just the tighter the orbit gets, because this can get arbitrarily close to the center of symmetry, which is 0 in the classical case. And so you can imagine orbits that are extremely tight in the classical case that do something like this. Just really get pulled around and get flipped around, right? That's a legitimate possible orbit in the classical case. And the higher the energy, the arbitrarily close you can get to the center, and you can still go back away on a flyby. That's no longer true in general relativity, because now all of a sudden we're dealing with this turnaround, this pit in the potential, right? And actually right now, I didn't even talk about this portion of the orbit. I've only talked about this exterior part of the orbit. We'll talk about these guys later. But now, if there's no stopping, there's no reason why you can't have energy up here, right? I mean, we're just talking. Remember, this is just the physical setup of the. This is just the physical setup of the orbit. So you can definitely imagine that, say we set up one orbit that does do a flyby, and in the classical case we set up an orbit that does a much tighter flyby, right? That orbit has an arbitrarily high energy, and in the classical case it does the flyby as we demonstrated. But in our new case, that orbit, that same orbit which would have turned around in the classical case and gone back, goes right over the top of the angular momentum barrier. There's no turnaround point. And in fact, what happens is as it starts to accelerate in this region, right? Because in this region, here it's accelerating. I'm sorry. It suffers deceleration in this region from here to here. It does decelerate in there just like anything else. But once it gets over there, it starts to accelerate again, and it goes right into the center. So that is no longer a flyby orbit, right? What happens in that circumstance is I guess I'll do it in green, is in the general relativistic case, what would have been the blue line in the classical case now goes like that, and it gets pulled right into the center. It gets pulled right off that hyperbolic path. Well, it probably wasn't on a very precise hyperbolic path to begin with, but it gets pulled right into the center. And if you look at it close, you would see an orbit that would go like this, like that. It can go, there's different paths, it can take different paths to the center. It can almost go straight in. It can orbit a few times and go in. It all depends on exactly the orbit that it's on, and we'll talk about that a little more in detail. But these orbits are not flyby orbits. They are called plunging orbits. All those orbits are destined to hit the center of the black hole. Notice I'm not really talking much about the event horizon, which is at 2m. Ultimately what I mean is they are going to hit the event horizon of the black hole. I talk about the center, which is 0, right? And that's the singularity. But we haven't really talked about singularities and event horizons yet because we haven't discussed the metric in detail. We haven't developed the metric and studied the space-time. What we're studying is the orbits, which is a little bit of an out-of-order presentation, I think. But that's the whole point of my technique here, is to do things out of order. So those are plunging orbits. What other orbits are around? Well, obviously you have these orbits, right? Oops, I want to do this in blue. You have these orbits, the orbits that have an inner turning point and an outer turning point, right? And those are the bound orbits. Those are the bound orbits. And you actually have to have a total energy less than your rest energy to get into a bound orbit. And from a distance, that's not possible to do, because if you're far away, your energy is, by definition, is going to be 1, because this potential is already pushing 1. So you can't be below 1 out here, right? This isn't quantum mechanics where we can play around with being in the wrong being in the wrong energy zone, right, outside of the impermissible zone. This is classical physics, right? You can't be here. So in order to actually become bound, and this is true in the classical case as well, is if you fall in on some flyby orbit, you actually have to slow yourself down. You have to drop kinetic energy from, say, here. You have to drop your kinetic energy by turning on your rocket motors. Let's say this is your rocket ship here, right? You actually have to turn on your rocket motors and slow yourself down. You have to fight this acceleration, drop your energy, and then allow yourself to continue to fall around the bound orbits. But as you do that, as you turn on these rocket motors to drop this much kinetic energy, as you do that, you've got to make sure, if you're trying to be very academic about it, you've got to make sure you stay on the same angular momentum path. You can't turn on these, you've got to turn on these motors in such a way that you slow your kinetic energy, but you retain your angular momentum in order to hit this bound orbit. If you lowered your angular momentum, you'd actually be playing on a different curve, right? And you can still find a bound state in there, but you want to make sure you know what you're doing. It's not as simple as just slowing yourself down. You've got to slow yourself down in a way that retains the exact angular momentum that you have. So that's all orbital mechanics, right? But let's just presume that you can do such a thing. Then you can enter all of these guys in here, which are bound orbits. So so this is the same as classical physics. This is the same as classical physics. These plunging orbits are totally new and only exist in general relativity. And what's also important is that the shape of these orbits, the shape of the bound orbits, the shape of the flyby orbits, and the shape of the plunging orbits are no longer consistent with classical mechanics. Now consider for a moment a different angular momentum barrier. Consider this angular momentum barrier here, 1.88. So with this orbit, everything is sort of the same, except that now the angular momentum is so low that you actually open up a new zone. You open up a zone between here and here, right? Where there's these orbits that have outer turning points but no inner turning points, right? Again, something that doesn't exist classically. You still have the possibility of bound orbits, but now everything is plunging, right? Everything's a plunging orbit. There are no flyby orbits in this circumstance, right? I guess I should erase that to make it look like it. So now we have our plunging orbits up here. We have our bound orbits in here. And these guys are, they're definitely bound because they don't go to infinity, but they're also plunging. So they're like bound plunging orbits. And in both cases, we still have orbits that hit this inside, right? That hit this inside turning point. They're really a form of bound plunging orbit, right? Because there's really not much distinction between an orbit that does this and one that does this. The only difference is there's no, it's not passing over these bound orbits. But these orbits are given a different name. They're called near orbits. Near orbits. And there's a lot of issues with understanding near orbits because you have this event horizon here. And the near orbits actually cross the event horizon in both directions if you mathematically calculate them. So they're kind of interesting in that way. We'll be talking a little bit more about them later. So that's the situation as it is with general relativity. And understanding this chart is really important because we're going to use it to help us understand how our equations work. So next time we're going to now associate these different orbits with our basic equation our radius anomaly equation. So the equations we're going to work with from the list of radius anomaly equations are really these four, and actually for the rest of today's talk at least, and probably for the near future, will be the factored forms of these two equations. So we're using Costic's chi equation, which that's my name for it, and the reason is because the paper by Costic is where I learned about this, and he derived it this way. And then the factored, I'll call it the p equation, but that's the Weierstrass function that we talked about previously. So what we're doing is we're taking these factored forms, and what's just important to remember is that in the original form of the equation, the initial conditions, which meant the constants of the motion, essentially, were wrapped up in various constants, and we talked about how those constants, what those constants actually were. In other words, A is a function of the angular momentum and the initial energy, and as well as the so-called the mass of the star, and likewise. That information gets transmitted into the roots of this expression, right? So if you know this form of the equation, you know A and B, you factor it, you expand the inside of this thing, and you factor it, and you get three roots. And you can always do that. It's a cubic equation. It can always be factored. Likewise, in the p equation, all the initial conditions are wrapped up in G2 and G3, and likewise that information flows into the roots. Now there are three roots, but only two constants of the motion, and that's because not all three roots of a cubic equation are independent. If you know two, you can quickly calculate the third, and as I pointed out before, that's manifested in Chandra's form, where the three roots are all a function of two things, the eccentricity and the semilattice rectum. So knowing the roots should tell us everything we need to know about the solution. The problem is that there are many different possible combinations of roots. Generally speaking, we're going to always align the roots so E1 is greater than E2, which is greater than E3, if all three roots are real. If not, then the real root will be E1, and then E2 will obviously be the conjugate of E3. And so not only do we have those two possibilities for the roots, but then we have various relative values of E1, E2, and E3. We have their relationship to 0. Well, in this case, relationship, we'll see in a moment, it's to minus 1/12. Obviously, these roots here are related to these roots here just through this expression here, as I explained before. These two equations are essentially the same, except for the fact that they've been transformed by this linear transformation, which is traceable back to classical algebra, which gets rid of the squared term, right? There's no u squared here in this differential equation. So ultimately, all of the orbits are determined by these roots, and I made this chart here that illustrates this. It illustrates it for those two equations. Remember, the roots of the factored chi equation are u, and the roots of the p equation are e. But these are equivalent statements. I just put them both here on the same chart. But all of these, so if you have two types of potentials too. You have a potential where this peak occurs above the asymptotic limit, and you have a type of potential where that peak occurs below the asymptotic limit. So there's two types of peaks. And again, all of that, those peaks are dependent on the angular momentum of the system. So you would expect that flows into the roots, ui and ei, and it's captured by the roots. So the type of roots you have will also tell you what kind of angular momentum barrier you're looking at, or potential curve you're looking at. So imagine for a moment that the roots are such that, I'll blow this up, that u1 is greater than u2 and u3 is less than 0. And you're also presuming that chi is between u2 and u3. That's important because there's a turning point here, right? These roots represent turning points, so chi has to sort of be constrained between two roots. And in those circumstances, you're dealing with these scattering orbits. These are objects that are flying in, have sufficient angular momentum to scatter off the black hole and then return to infinity. However, if you now deal with the region where chi is greater than u1, instead of constraining chi to be between u2 and u3, u3 is not really a turning point, right? It's a turning point in infinity. But if chi is greater than u1, that actually translates, because remember, chi is ultimately related to 1 over the Schwarzschild radial coordinate. Then in that circumstance, you're dealing with orbits on the inside, right? On the inside, these are the near orbits. And these are, I can't call them near scattering orbits because you've never really scattered from infinity. They're just near orbits that are above the asymptotic barrier, but inside and behind the angular momentum barrier. And likewise, these bound orbits are the circumstance where u1, all three are real. That's a good point, right? All three of the roots here are real, and they can be put in order, and e3 is less than minus 1/12, which is equivalent to u3 being less than 0. In the same circumstance, all three real roots, e3 is now greater than minus 1/12, and u3 is greater than 0, and you've got chi constrained literally between u2 and u3. And those are bound orbits that have an inevitable angular momentum barrier on their left and a part of the angular momentum barrier on their right. So that's bound orbits when this potential actually comes above the asymptotic limit. Now, there's also the possibility of the potential not going above the asymptotic limit, but you still have bound orbits that are constrained by the potential on both sides, and that's in that circumstance will be these regions also for those angular momentum potentials, or for those effective potentials, you have the same condition. However, for these potentials, you also have this condition here where you're below the asymptotic limit, but unbound on the side, unbound by angular momentum as you approach the star. And that circumstance materializes because the root relationship is all of a sudden E2 and E3 are complex conjugates. You have complex conjugate roots now, and E1 is still greater than minus 1/12. So that reflects this part here is similar to the bound periodic orbits, but now two of the roots are complex conjugate pairs, and that brings you into this region here. With the larger angular momentum barriers, that region doesn't even exist. However, the only region that does exist is complex conjugate pairs, but E1 is less than 1/12, and that is these unbound plunging orbits. Orbits that are unbound and plunging. Those only exist in general relativity, will not exist in Newtonian mechanics. Because again, in Newtonian mechanics, it is inevitable that this will have some appearance like that and go up forever and ever and ever, and there will always be a piece of the angular momentum barrier over here to keep you unplunging, or to prevent plunging. Okay, so that's where those guys would come from. And the condition, by the way, is the same for this potential curve too. For this style of potential curve, you have the same condition for that. But what else do you have? So you also have, then you have near orbits that are, let me point to it. There are near orbits that are below the asymptotic limit, but above the minimum of the potential, or the local minimum of this potential, this little bound well. And those orbits are characterized by 3 real roots where, but now U is taken to be greater than E1, right? U is taken to be greater than E1, as opposed to these bound circumstances where, I'm sorry, all right, let's think about it in terms of chi. Chi is taken to be greater than E1, or chi is taken to be greater than U1. Here, chi is taken to be bound between U2 and U3. So those would correspond to these positions. Now remember, this is rho. So rho is 1 over chi times, actually, I should write it this way. So rho is alpha over chi, right? So when I talk about the turning points here, they correspond to, they're corresponding to the Schwarzschild coordinate in the diagram. So you have to kind of make that correction. But regardless, there's 3 of these things, right? And when we're talking about chi is greater than U1, it actually talks about chi being in this region. So chi will now correspond to a rho reciprocally. So it's small radial distances, even though it looks large. Here, it's greater than the largest root there, but that's chi. So rho is going to be smaller than this. And you can make that transformation separately. I mean, it's not that difficult. Likewise, there are near orbits on this, for angular momentum barriers that go above the asymptotic limit, there are near orbits in here as well. And in those cases, it absorbs all of these rules, but again, chi is greater than U1. This region here doesn't exist for this angular momentum barrier. So you get introduced this new region here, but you lose that region there. And then you can have near orbits that are so low in energy that they're below any possibility of being bound, and they're way, way down here. And that seems to be the case when E2 and E3 are complex conjugate pairs, but E1 is less than minus 1/12. And those exist here as well, and I think they have the same rules. Yeah, the same rules exist here too. Anyway, so now the point is the roots inform us what type of orbit we're dealing with. And ultimately, all of these roots determine the shape of the orbit, the real shape. And this chart is really good to reflect how these orbits actually look. So consider this orbit here, which back here would be an orbit in the bottom of the bound well. So basically, 2 of the real roots are becoming equal, right? So U2 and U3, for example, are becoming equal. Well, that would be a circular orbit, right? Right there is the only place where you get a circular orbit. Very similar, by the way, to classical mechanics. Now, if you increase the energy a little bit and you start orbiting right here, you end up with orbits that, and the light gray shows the full orbit, and the dark part here shows sort of one iteration. But you'll notice the orbit doesn't close on one iteration because famously orbits in these kind of potentials precess. And here you literally see the precession of this orbit. It's interesting. This one precesses, in 2 steps, and then, it just precesses wild. This is literally the way the orbit, this is the actual orbit, this faint line. So it's very complex precession. Mercury has a very, very small precession. It's like right above, it'd be just a little bit above this perfect circularity, and it's a tiny precession. But here you have a big precession. And as these bound orbits get higher and higher, here's one right under the unbound limit, right? And if you look at its precession, it's absolutely insane. It goes, that's one iteration of the orbit. It's precessed from here to here in one revolution, so to speak. And ultimately, if you end up with E equals 1, you have this perfect flyby orbit, but notice that it crosses itself. It crosses itself. That's really fascinating that it does that. And then as the energy gets higher and higher, as you start bouncing off this angular momentum barrier, you end up with these kind of orbits here. These orbits that cross, but the closer you get to the top of the angular momentum barrier, what you start seeing is the orbit will fly by, spin around twice, and then fly out. Right? It starts doing this multiple orbit flyby, and the closer you get to the tip, you can make an arbitrary number of revolutions before it flies out, which is completely fascinating. But if you just come right above the angular momentum barrier, now you're in a circumstance where you come in from infinity, right? These are all flybys. You come in from infinity, you go back to infinity. But you come in from infinity, and then you orbit, and then you collapse right to the center. And you can orbit an arbitrary number of times, depending on how sensitive you are to, how close you are to the tip of this barrier. Often you hear it said that the last circular orbit that's possible is 3 Schwarzschild radii from the black hole. So 2 is the event horizon, so you can't orbit there. But if you're freely falling and you're just riding the crest here, you can orbit in a circular orbit right around the black hole. But it's totally unstable. If a little extra energy and you fly away, and a little less energy and you get pulled in. So it's an unstable orbit. So the last stable circular orbit is here, but the last possible circular orbit, which is unstable, is there. And as angular momentum increases, by the way, this point goes towards 3 Schwarzschild radii, and that's called the photon sphere. Anyway, you start increasing your energy, and then you get these plunging orbits, right? They just come from infinity, boom, they just plunge right in, and they stop making these. This is a plunging orbit too, but they become less and less circular around the black hole the higher energy you have, and eventually they just plunge right in. And then there's a similar set of charts. These near orbits can also be calculated. And this chart kind of shows that story. So here we're dealing with a potential where I just picked one where the tip was below the angular momentum barrier here. And again, you have the circular orbit right here at the minimum. This gets a little grainy the more I blow it up. Sorry about that. And as it increases, you start seeing these bound orbits that have... notice how this bound orbit works, by the way. You have this sort of inner pass, and then you have an inner pass, and then you have a bigger pass, then you have an inner pass and a wider pass. So that's totally non-Newtonian, completely non-Newtonian. You can't have that in Newtonian physics. And then as you hit this part, you hit this barrier here, the tip of that barrier here, you're bound on the outside, but you're unbound on the inside. Again, totally non-Newtonian, and these orbits have this kind of appearance, right? As long as they're bound, they swing out from the far point, the apogee, they come in, they orbit around the perigee a whole bunch, and then they pop back out to the apogee, and they precess also. Really fascinating orbits. But the near orbits are cool, right? So the near orbits will start from here and then just plunge into the event horizon. Now, what I'm not showing here is that if you do the actual calculation of the solution of the equation for the near orbits, it actually comes down in here and it comes back out. And then it goes in and out. So it's crossing the event horizon willy-nilly, mathematically speaking. But we're physicists and we don't think it ever comes out. So I'm just drawn it so it hits the event horizon. Likewise, as you creep up this angular momentum barrier, you start getting into, again, circularity. If you come really close to the top, it may orbit a few times and then come back. But all of these things are, as long as you're on this side of the angular momentum barrier, you'll come in, and mathematically you'll spin around and come back out and keep doing it. But the truth is that you hit that singularity. When I say mathematically, the math doesn't stop you just because r equals 0, right? The math says r equals 0, and then r is more, and it's still in orbit. But once we, as physicists, say once you hit r equals 0, you're stuck. And actually, furthermore, as physicists, we say, yeah, and you're also never coming back out of this event horizon. And that's a totally different question that we'll talk about eventually. And then you have these plunging orbits at these unbound plunging orbits, and they come in from a distance. And as your energy goes up from here, I guess these thin lines show you start circular, and as your energy goes up, you become, more asymmetric and interesting, and then you finally get in this weird position where you're processing wildly, and then ultimately at, let's see, how have I done this? So here, this guy here is at 0.9854, which is, for this circumstance, is right below that height. Or the maximum is at 0.9854. That peak is at 0.9854. So this orbit is 0.9850, which is a little bit below it. This one is right there at 0.9854, and you can see it has this big orbit, and then it has a lot of orbits around it, but it's still below that tip. So I calculated it just below that tip, just to show that it'll come back in and orbit a whole lot, and then come back out again. And then, but as you go up to 0.990, now you start to collapse. This thing stretches out and just collapses into the black hole. And you start having these plunging orbits. And then the first unbound plunging orbit happens at 1. So if you keep this up, this tail of the bound part gets farther and farther and farther at, and finally when you're at 1, it becomes limits to this plunging orbit. The near orbits also have this property too, right? This thing, the near orbits, as your energy goes up, become tighter and tighter and more circular right around this tip. Anyway, so that's another picture about how these orbits look. Another thing about this chart is it shows you, again, how you interpret this potential chart. The paths look like they come in and bounce out, but of course there's also, this is the radial direction, right? The radial direction. So there is a period of time where you're accelerating radially, but then you start to decelerate. Now your velocity is actually very high in here, but your radial velocity actually becomes 0 at the turning point. So you have to really understand what this potential chart means. And this kind of potential chart shows up a lot in quantum mechanics and electromagnetism, and we see it a lot. We have to understand that there's a picture. There's an actual picture of an orbit involved. This is that orbit, right? You start out with R very, very large. R gets very small. The R actually, the change in R is 0 here, right? So your radial velocity here is actually 0, but your actual velocity is quite fast, or it's at a peak probably. As energy is still conserved, that's the beauty of the Schwarzschild geometry, is that you can still draw this one-dimensional potential and still talk about the orbits. As soon as you lose perfect spherical symmetry, all this goes away. You can't do this for a Kerr black hole, for example. It's much more difficult, and I'd like to try it. I'd like to try showing you how it all works for a Kerr black hole, but boy, that'd be like 100 lectures from now if I did it. Anyway, so now the rest of this part of the course, I really think it's interesting to understand how these orbits are kind of calculated. And I think it's fully described in the book I'm offering to Patreon members, Why Does It Move? But I think I'll spend a little bit of time going through how that process is done to calculate these actual things. Because that's what fascinates me, is how do you actually calculate this path? These aren't guesses. There's precise equations that describe these paths, and those equations are, of course, the very equations that solve these differential equations. And so, and we've already shown what one of them is, the p function. The p function we know solves this equation. Therefore, and we actually converted the p function using this to show what we know the solution of these equations. But we can actually do it a little bit more practically, and I think that's what we'll begin in our next lecture.